Okay, so let's continue on with part 2. Now remember, for part 2, what we're working on here is we're trying to find the angle between two vectors. Now, like I said in part 1, direction is important. You either want the vectors heading away from each other or towards each other. If they're going head to tail, you're going to look for the supplement of that because you'll be finding the wrong angle there. So first things first, to make sure, we always want to make sure we graph the vectors out. So we want to find the angle between vectors u and v. So same two vectors that we saw up here. So the first thing I do is I'm going to graph them just to make sure I'm going to get the right angle when I solve it. Alright, so let's see here. So I want to find the angle. So vector v is at 3, 4, 3, 4. So there's vector u, or vector v. Vector u is at negative 2, 6. Down to negative 2 up to 6. So if I look at the angles, they are heading away from each other, which is good, and that's what I want. So to find my angle, I'm just going to take the cosine of theta equals the dot product of u and v, 3, 4, dot that with negative 2, 6, and then I divide by their magnitude. Well, the magnitude here, let's see here, the magnitude of the first one, that's going to be 9 plus 16 times the magnitude of negative 2, 6, that's going to become 4 plus 36. So if we simplify this all out, we get on top, we're going to get 3 times negative 2 plus 4 times 6. Divide that by 5 times 40, root 40. So we get a top, what do we get? 6 plus 24, we get 18 over 5 root 40. Now, right away, I actually already know something. The reason why we like cosine is for a special reason. Because cosine, if we think about it, cosine is positive in the first quadrant, negative in the second quadrant. So it's going to cover all angles from 0 degrees all the way to 180 degrees. And of course, in the middle is 90 degrees. Cosine is nice because if I see that this is the cosine of theta, I already know that this angle, that theta, I already know that theta is going to be between 0 and 90 degrees. And I know that because this is positive. If this were negative, I know that this would be an obtuse angle. And so it's very kind of simple to do. It's very simple to kind of understand. That's why we like cosine. Sine doesn't work that way for us very well. So if we were to solve this using our trusty calculators, we would get theta equals roughly 55 degrees right there, if you solve that on your calculator. Now, what if the two angles were perpendicular or orthogonal? Then what would their dot product be? Well, that's kind of interesting, because if I know that it's cosine, well, if they're perpendicular, remember orthogonal, remember perpendicular, orthogonal is another word for perpendicular, I know that the cosine of theta has to be what? 0. Well, where would that go on top here? If I think algebraically, well, the 0 can't go on bottom. Bad if 0 is on bottom, so the 0 would have to be on top. And the top is my dot product. So I know that the dot product would be 0 if they are orthogonal. So if I want to find out which vectors are orthogonal, and this is we do this all the time. Think about a right-hand rule. If we're looking for where vectors are orthogonal, I don't have to do the entire angle rule. I can just look at their dot product. So I'm looking for 90 degrees. So I can just look at their dot product. V dot u. And that's going to give us 2, 5, dot that with negative 10, 4. So that's going to give us negative 20 plus 20, which is 0. Because that's 0, therefore I can say V and U are perpendicular or orthogonal. Now, One thing I want to see, when I write my u's, I tend to look a little foot on it there. Kind of helps me distinguish. Sometimes mathematicians, their v's and their u's tend to look alike. So we tend to put like a little hook on the u at the end. So let's try this one. V dot u becomes negative 3, 4. Dot that with 4, negative 3. And if we do that, we're going to get, what's that, negative 12. What's that? Minus 12, which is negative 24. Ooh, that doesn't work. So therefore, these are not orthogonal. But I do know something. It's not orthogonal, but take a look. Now the bottom is always going to be positive. See, the magnitude is always going to be greater than 0. Magnitude is always greater than 0. So my dot product is negative. So even though I know this is not orthogonal, I know this angle theta is between 90 degrees and 180 degrees. I know theta has to be between there. In other words, this is going to be an obtuse angle. I can say for definite now, I know that V and U are the angle is obtuse. Because I can just look at that angle there. I can just look at that number. All right. Now, a lot of times we can graph these in 2-dimensional, but the problem occurs is if this happens in 3 dimensions. So another way we can determine if vectors are orthogonal in 2 dimensions is we can use slope rules for perpendicular lines. Okay, so I can even use my old Algebra 2 stuff. For example, let's take a look at or my geometry. If I look at vector V is 2, 5, right? In other words, if I write that as a slope, it is 5 over 2. If I look at vector U, which is this negative 10, 4, my slope here would be 4 over negative 10, which is negative 2/5. Notice these are opposite and reciprocals. Therefore, they are orthogonal. And when we think orthogonal, remember, we are really saying perpendicular right here. Now, this is nice. Whoops, sorry, you can't even see that. Excuse me. Sorry. This is really nice in 2D, but not easy to do in 3D. Matter of fact, in 3D, it's almost impossible. So we don't even do it. We must. So therefore, in 3D, you must use the product rule in 3D. Okay, we're going to go and stop section 2, part 2 here, and if we go into part 3, we're going to talk about another application, which is called a projection. And I will see you guys later. Bye.